Hey, welcome back. So, since the beginning of the course, we've been talking about capacitors, and capacitors, I'll remember, are a device that has the capacity to store electric charge, in particular electrical energy. And we use that primarily because they're got a nice uniform electric field that only extends in one direction. So it's something that we can introduce the concept of electric fields with very easily. However, capacitors, the device, is one of the single most used, other than maybe ICs, integrated circuits themselves. It's one of the single most used electronic components that you can find in the world because they're so versatile. So a capacitor is a device that can store energy and discharge it then at a later time. Now, you might argue, well, okay, Dr. K, that's just a battery, right? A rechargeable battery? Sure, you're not wrong. However, a capacitor can store an immense amount of charge, much more than you can put in a single battery. But more importantly, it can discharge that at different rates. And so the classic example of this is a defibrillator. So with a defibrillator, the heart requires a lot of electric charge, a lot of energy in order to restart it, to get it going. And it has to be issued in a very short period of time. Well, there's no way you can get that amount of charge in the time you have if you just, plug the device into the wall or a battery or anything like that. So what we do is we spend maybe 10 seconds or so building up charge in a capacitor. And that's that whine that you hear. The sound's actually being made by the device just to warn you it's charging. But once we've done that, then we flip a switch and we change what we call the time constant, how fast we can discharge that. And so then it dumps all of that charge into the heart very, very quickly. And that's what that little switch on the paddles is doing when you yell clear, and you zap them. Another common use is a survival flashlight, if you've ever seen these before. So what they are, they don't have a battery in them. They've got just like a magnet ring or a electromagnet effectively, and then a piece of iron that can shake back and forth. And so you shake the flashlight, and what that does is it charges a capacitor. There's no battery in it at all. The LED that's in there requires very little charge to run. And so when you turn it on, it just slowly drains the charge out of the capacitor into the LED. As soon as your capacitor is dead, well, you turn it off and you shake it up again, and you're ready to go. The advantage to these, if you leave a battery around, it's going to become dead even if you never use it over a long period of time. So sticking a flashlight in your car may not be helpful if the battery's dead when you need it. The advantage to these is you can always charge that capacitor fairly quickly, and since you don't need much of the LED, it'll last a pretty good while. So we're going to be working with capacitors quite a bit. One of the other common devices that we'll use, and we'll talk about this one in detail, is a filter. If you're an audiophile and you like to listen to good music through speakers or headphones or anything like that, you may have sometimes heard if there's like a pop or a hiss or something in the background. That's noise in the signal. That's noise in the data that's being sent to your headphones. So what we can do is we can use a resistor and a capacitor together so that it takes time for that capacitor to charge. So let's say that I'm getting a big jump in the noise that's there. Well, the capacitor doesn't respond to that right away. And by the time the capacitor has responded, it's already gone. And so it has the end result then of smoothing out that signal, so you get a much higher quality. And it's called a bandpass filter. We have high pass filters and low pass filters and things like that. So they're extremely useful. So what we're going to talk about in this lesson here is we're going to talk about their physical properties and also how much energy is actually stored. When we talk about capacitors, we want to think of two things. First of all, there is the definition of the capacitor, and we'll talk about that in detail. But then there's also the construction of the capacitor. So keep those two things in mind. The doctor or the scientist or whatever may say, hey, I need this amount of charge for this amount of voltage. And you, the engineer, would say, oh, okay, well, I need to have this much capacitance. Now that I know the amount of capacitance, what I'll do is I'll design, okay, how do I make these plates in a way that will give me that capacitance that will store the charge that the user actually wants. So keep that in mind as we go through there. All right, let's get started. All right, so to get started, let's draw that capacitor circuit that we've been using for most of this semester here. So I'm just going to draw the two plates as thin plates. We'll see why that's important in a minute. And then that's going to be connected to a battery, where this is the negative end of the battery, and this is the positive end of the battery. So those charges are separated temporarily. So remind yourself, how are these plates going to be charged? So any electrons are going to get repelled away, and that's going to give this a negative charge, like this. Positive charges, remember, don't move through here. It's attracting the negative charges. And so that leaves positive charge behind. Okay, so keep that in mind. That's real important. Now, based on Faraday's rules, what does the electric field look like? So the question in your book says, how does the electric field vary from left to right between the plates? Well, if we're going to draw the field lines, remember that it goes from the positive to the negative. So it's going to go straight across like this. And so how does it vary from left to right? Well, also Faraday's rules say that the closer these lines are together, the more dense these lines are, then the greater the electric field. Does it change throughout here? No, it's constant. And we've been using that up to this point. We've been saying, okay, yes, I've got a constant electric field through here, so it's not changing at all. So how does the electric potential across these plates? Now, on this little side note, I'm actually going to be a little bit lazy here. Technically, it's always a potential change. But remember that we said that we're going to define the negative potential to be 0. So by the time I jump across, my change in potential is just going to be the potential of the positive. So anytime you see me write voltage or volts or talk about a potential, we're really talking about a potential difference. This is why if you're building a circuit, you've got to have both that positive and negative lead or it's not going to connect. All right, so let's say that this is, for example, a 9-volt battery. What is going to be the potential difference across here? Now, we've talked about this before. Well, it's still going to be 9 volts. So the potential difference across the capacitor plates, while it's connected to the battery, and that's going to be important later, while it's connected to the battery, is going to be the same as the battery. So I build up this same potential difference because of the electric charge that's building up on there. All right, so we want to find the electric field around that's produced by one of these plates. We're going to look at them individually. So let's just clear this off for now. And this is scenario 1 in your book. I'm going to draw this in 3D once, and then we're going to switch to a 2D view because, well, I don't draw in 3D very well. And something like this. So here's my plate. And it's going to be a very, 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 very thin plate. All right. Now, we can idealize this as an infinitely thin plate. Now, in the real world, obviously, infinitely thin plates, two-dimensional objects, don't exist. It's always got to have some sort of thickness. And for an engineer, it's not good enough to just say, oh, yeah, it's an infinitely thin plate. We have to have some condition that has to be satisfied. And so in this case, let's say that, going back to my circuit here, if this is my capacitor, if this distance d, which is the farthest distance I'm going to get from the plate, if that distance d is much, much less than the length of one side, remember, it doesn't have to be the same, but L and L, as long as it's much, much less than the smaller length, then I don't make any detectable error by saying, okay, yeah, it's just infinitely thin from that. And it just simplifies our calculations. But always remember to check this. If that expression, if that d much less than L doesn't hold, I can't use this approximation that we're using. It's going to work for a lot of times, but you always need to be aware of when it might not, because that's when it's going to jump up to bite you. Okay, so I'm going to draw it from the side here. And so we want to draw let's say that it's negatively charged. I'm going to live with the negatively charged plate. So we've got all these negative charges here. That's this one right here that we're looking at. And remember, it's going into the screen. So it's a 3-dimensional object sticking up out of the screen there. So we wanted to figure out what is the electric field at that distance d away from it. Okay. So now this is an infinite plate. So the charge, it's going to be hard for us to specify. So what we will normally specify is we'll talk about a charge density. And you've probably dealt with densities before. Probably the most common one that you've dealt with is rho, and it's probably a mass density. So you may have defined a mass density to be simply the mass divided by the volume. Well, for a charge, it's the same thing. A charge density is the number of coulombs divided by the volume. And I'm going to use this V with a line through it to represent a volume. The reason for that is obviously because we're going to be using V for voltage all the time. And so we need to have some sort of distinction between the two without having to always spell it out. So the number of coulombs per cubic meter, for example, the charge per cubic meter. So let's use our general variables here. So here's our units then are going to be coulombs per meters cubed. And rho then we can write as being some symbol Q, the total charge there, divided by the volume. The reason that's handy then is if I want to know the amount of charge in any particular volume, rho is the same throughout this. And you've probably experienced this before. If I have a rock, let's just, that's a rock. And let's say that rock has a density of, say, 5.5 grams per cubic centimeter. Then that density is going to be the same everywhere throughout this rock. So any little chunk that I take has that same density of 5.5. If I want to know how much mass is contained in here, all I need to do is multiply this density by the volume of that little chunk, and I'll have the mass that's in that chunk. But rho itself is the same throughout. Okay, so that's a volume charge density, or volume, that was a mass, and then volume charge density works exactly the same way. What you may be less familiar with are the other two. So this lowercase letter sigma we use to represent an area charge density. So that would be Q divided by the area. And so that'll have units of coulombs per square meter. And that's what we're going to work with here. But then let's go ahead and talk about this other one we've introduced before. And so the line charge is going to be lambda, which is Q divided by the length, and so it has units of coulombs per meter. So if you don't remember that, it's probably worth going back and reviewing that. We introduced this idea when we talked about infinite lines going through here. All right, so for this example, let's suppose that you have been given the area charge density for this particular plate. All right, and so I know what this is. So that's some value, and it's given to me, and that's going to be in coulombs per square meters, like that. All right, and I want to know what is the electric field at some distance d from that plate. And hopefully you can see why we would want to use that, because that's going to be where my other plate is, where my positively charged plate is going to be. So that's going to be our interest that we have in that. All right, so let's derive an expression, and let's use Gauss's law. So first thing I want to do is I want to draw my Gaussian surface. And you can use anything you want. You could use a box, you could use a cylinder. It's actually not going to make any real difference as long as it's something that, one, we can integrate, we can find the area of, and two, the electric field is going to be constant. So we've used a cylinder before, so let's just go ahead and use a box this time. So that box is going to cross right here, and then it will extend down this way, and then up this way. So try to envision that this Gaussian surface, this box, is puncturing through that plate from there. Okay, so we set this up exactly the same way we've been doing Gauss's law all along. I'm going to switch back to black for this. And we're going to go ahead and jump straight to Gauss's law is the charge enclosed divided by epsilon naught. And remember, that's actually the flux. That's the electric flux. But then the definition of the electric flux is the surface integral of the vector electric field dotted into the vector area. So remember that the area vector is perpendicular to the surface. And I'm not talking about this surface. I'm not talking about the surface of the plane here. I'm talking about the surfaces of the Gaussian surface here. So don't get confused. A lot of people get confused when they think about that. So my area vectors here, I've got one this way, I've got one this way, I've got one this way, and so on. So the area vector is going to be perpendicular to the surface. Okay. So let's see where we would go from there. So we've set these equal to each other. First step then is going to be to do this, to do the dot product here. So I get Q enclosed over epsilon naught is going to be equal to, doing the dot product, we get E dA cosine theta. Okay. Now I have to add up all the parts that contribute, and it is perfectly okay to write out for each face. Now we only had 3 parts for the cylinder, but if you think about it here, I've actually got 6 different faces. I've got the ones on the sides, that's 4, then the top end cap and the bottom end cap. But before we go through all that work, let's think about it. These sides here, the electric field, remember, is going to be coming out like this. And I'm going to draw that on my 2D picture here. So it looks something like this. And whoops, these are negative. So if I'm going to do the negative side, we had better make those lines come in. So let's be real careful about that. So we're going to make our lines go this way, right? Because Faraday's rules say that it should land on the negative charge. So that goes like that and that and that and that. And then drawing our Gaussian surface in here, that's going to be a box. And so I'm just going to make it solid so that we can see it. So that's that box as seen from the side. And you should be able to see that it's the charge enclosed is only this area right here. Okay. So now my electric field, my area vector for this is this way. And you see that my area vector is perpendicular to my electric field. So cosine of 90 is 0. So already we know those four sides of that box don't contribute anything to the flux that we're looking for. So they're already 0. It's okay to write them out and then make them 0. And while you're first learning, that's probably not a bad idea. But hopefully you're going to get to the point where you can see, oh, right, only these two end caps are going to contribute. I've got flux coming into them and I've got flux going out. So remember, it's going to look something like this. Okay. All right. So for the end caps, the electric flux is in the same direction as my area vector, or as my area vector here. So that means that cosine theta is going to be 1. We've done all of this. Go back to the using Gauss's law lecture if you want to get some more experience with that. So simplifying this a little bit, then we get Q enclosed is epsilon naught times the integral of E dA, where neither one of these are vectors. These are scalars now. Well, the whole point of this was to make sure that E was constant on that Gaussian surface. You chose the Gaussian surface so that it's constant. So that means I can pull this outside. And I'll just write it here. So that's going to be E times the surface integral of A. Well, the surface integral of dA is just the area. Be very careful. This is the total area of the Gaussian surface. But I have one here and one here. So I actually have two of those areas. And these areas, by the way, are the same as the area that it's crossing the main plate with. But so I've got this area and I've got this area. So if I call this A, then I must have two of them. Now remember, this is not the area of the plates. This is the area of your Gaussian surface. So since you chose it, it had better cancel. If it doesn't cancel, we've got a problem. So just keep that in the back of your mind. All right, so we'll write this then as E times 2A, because I have two of those plates there. Does everybody see why? All right, let's solve for E. And so I get that the electric field, the magnitude of the electric field, is going to be Q enclosed over 2A epsilon naught. So now I need to get rid of my Q because I don't know how much Q is here. All I have is this area charge density. So we'll start with our definition of the area charge density. That's going to be Q divided by the area. Now this area here, though, is the area enclosed, which might not be the same exactly as the area of my Gaussian surface. In this case, it is. That area happens to be, this area here happens to mathematically be the same size as this area here because I simply chose a box. So keep in mind, in this case, then I can say Q enclosed is over area because it's all the same, not because it's the same thing. These are the areas for the Gaussian surface. This is the area for the charge that's enclosed within that Gaussian surface. May not seem like an important distinction, but it will eventually to keep you on track to keep that separate. So I'm going to solve this for Q, and I get that it's going to be simply sigma times A. So we'll go back to our expression here, and so this is sigma times A divided by 2 over A epsilon naught, and whew, my areas cancel. So the electric field then of a single thin charged plate is going to be sigma over 2 epsilon naught. And if you did the homework from last time, that should look really familiar. Okay. So focus on the technique, but now we're applying that technique to an actual situation, one that's going to work. That's going to work for me. Now, on the next page, we talk about how would this be different if I had a thick plate. Got a little bit of a beef with how it's done in the real world. In the real world, if I have a thick plate that's a conductor, for example, I want to go ahead and just make a thick plate like this. If this is a conductor, where does the charge live? Remember, in a conductor, the charges are free to move. So they're all going to repel each other. And that's going to be true for any conductor. The charge is only going to live on the surface. It's going to repel each other. So it's all on the surface from there. So to a certain extent, you could say, oh, okay, wait a minute. I've actually got two charge plates here, right? So there's two ways to think about this. You can say, okay, if I define this to be a true area charge and be that density of the top, well, I've actually got two surfaces, don't I? And so I would have to say I've got this one plus this one to get the total Q enclosed. I would have to have a 2 here, right? Because it's a thick plate now. And so that, if you work back through the math, you're going to find that it works out very similarly, but now you're going to get something that looks like this, because that 2 is going to cancel. So that would be for a thick plate. Okay, my beef is this. I'm using an area charge density for something that is actually should be a volume charge density. Sometimes when they define the area charge, they're actually explicitly saying, okay, that's the charge stored on both of these plates added together, divided by the surface area of one of them. I've got a problem with that, and I think that's very confusing, and I think it's actually not even accurate with that. So in general, in this course, if we have an actual volume charge, I will use rho. And so you will need to know the thickness of that plate, the width or whatever it is. So I will use rho, and that would be then Q divided by the volume. I will not use sigma, the area charge density, to represent something for a thick plate. We'll just be nice and specific about that. We'll always just use rho. Something to keep in mind. But you need to be prepared for when you get out in the real world. You're going to see this pretty much all the time. Okay? All right, so let's analyze what we've got with this expression here. Let's go ahead and move the rest of this off the page here for just a minute. So let's copy it down a little bit neater. So we've got E is sigma over 2 epsilon. Okay, so here's my circuit. I've got my capacitor, and it's connected to my battery like this. All right, so the question says, keeping the capacitor connected to the battery, suppose you were to bring the plates of the capacitor closer together. So maybe we'll call this D initial, and we'll call this one, where they're closer together, we'll call that D final. And here's my battery right here. So we want to know what's going to happen. First of all, it says, how is the potential difference across the plates of the capacitor going to change? Stop the video, think about that for a moment, because that's kind of an important concept that I want you to think about. Okay, so just to make it a little more concrete, suppose this is a 9-volt battery. What would the potential difference across this plates be? It's just 9 volts. Keep that same 9-volt battery here. What's the potential difference across these plates? Still 9 volts. So as long as I keep that battery connected so that I'm keeping that potential difference the same, then changing the plate spacing doesn't affect anything. The voltage is going to be constant in both cases. All right, now what's going to happen to my electric field in this case? All right, so now we want to think about how things are changing. Now we need to look back in our notes, and we need to think about an expression that we had for the electric field of a parallel plate capacitor, not of just one plate, which is what we have here, but for a parallel plate capacitor. Look back through your notes and see if you can find it. All we're interested in right now is the magnitude. Pause the video and take a look. You really need to get in the habit of looking this up. So when you look that up, you should see that for a parallel plate capacitor, we talked about this relationship, where E was the electric field, D was the separation between the plates, and V was the voltage. Well, okay, we said the voltage is staying still, so we want to know what's going to happen to the electric field. So I'm going to solve this for E, and E is just V over D, as we've done before. So ask yourself, if D goes down, right, what has to happen to the electric field? It has to increase because they are inversely proportional, the D's in the bottom. So by bringing those plates together, I'm not changing the electric potential, but therefore I am changing the strength of the electric field. So the electric field is going to be stronger in that case. All right. So look on the next page. It says, what would happen to the area charge density in this case? So let's go back. Let's keep walking back through our equations here. We know that the area charge density on one of the plates, let's do that in black. We know that the area charge density is going to be Q divided by that area. Can you see that? So I have already defined that using this. So we're going to plug this one down here. So this has increased. So the electric field has increased. So what has happened to the area charge density, which we're going to plug in down here? Well, this one must also have increased. So my area charge density has increased. However, the area is constant. So if I look at this part right here, the area is still constant. So that hasn't changed. So if the area charge density has gone up, what has to happen to the total charge stored on the plate? Well, it's got to increase as well because those are directly proportional. So let's kind of walk back through that. So we pushed the plates closer together. Because they were still connected to the battery, the voltage didn't change. We looked back in our notes and we said, okay, I know that the electric field for a capacitor, don't get confused, this is for a plate, one of the plates. For a capacitor, I have E times D, the electric field times the distance between them is the voltage. If the voltage doesn't change, if the electric potential doesn't change, and the distance between them went down, then the electric field between these plates has to go up. Well, now we want to focus on each plate here. So this is for one plate. So if the electric field went up, then that tells me that the charge density had to go up. Then finally, we'll come back down to the charge density here. If the charge density went up and the area stayed the same, then the total charge must have increased from that. So what this tells me then is if I want to design a capacitor that's going to hold the largest amount of charge, remember that's the job of a capacitor, to hold the largest amount of charge. Ask yourself, do I want a large area or do I want a small area? Look at the equations we have here. I want to have the maximum charge possible. So I'm going to keep everything else constant. Well, I want a large area. Do you see that? So, and if we want to solve that, let me get rid of some of my arrows here. So here's where my area. So I'm going to solve this for the area, right? And this is Q over sigma. So make sure we've done that right. Yeah. So as the area goes up, if I keep the same charge density, well, then the charge stored on it will go up as well. So they're directly proportional. So I want a large area if I want to store it. And then we just saw that I want a small plate separation. The smaller the plate separation and the larger the plate area, the more charge I can store in that capacitor. So an ideal capacitor would have these huge honker monster plates together that are very, very, very close together. Now, the problem with getting them very, very close together is something that we'll talk about later on. But air is a wonderful insulator. It works extremely well. And so you're not getting charges. Let's use a different color. You're not getting charges jumping across like that. That's why you don't get sparks in between your capacitor. It just stays on the plates. However, if the electric field gets high enough, then the air will actually ionize. It'll break down. And that's the point at which it does is because it's dielectric constant. But the air will eventually break down. It'll ionize. And so now it will conduct electricity and zap the way that goes. So if I increase this electric field too much by decreasing the distance too much, eventually I'll get a spark and it's going to fry my capacitor. It's going to explode dramatically on that. If you've ever seen a thunderstorm, that's basically what's going on. The rain has stripped out some of the electrons, and so I get a charge difference between the clouds and the ground. When that builds up to be high enough, then the dielectric constant of the air, which was an insulator to this part, it breaks down, it ionizes, and so now, zap, and then I can have this lightning bolt traveling between the two. So lightning is really just, it's a capacitor. A thunderstorm is a capacitor, and a lightning just means you've gone past the amount of electric field that you can have. So you're walking around in this giant capacitor every time you enter a thunderstorm. Okay. All right, so we've talked about how the physical capacitor works. Let's now formally define what I mean by capacitance. So I'm going to slide the screen over here to the side. So capacitance, which we will use the letter C for, is defined to be the amount of charge per voltage that I use. Notice that I'm using voltage and not volume. You can see why that V could get confusing. So the amount of charge per voltage. So the units then, ask yourself, what are the units going to be for capacitance? Well, the fundamental units are going to be coulombs per volt. The SI unit for that is called the farad, named for microfaraday. Okay? So the unit of capacitance is a farad. Now, you remember that a coulomb is an, oh my God, huge, big number. So a farad is also a huge amount of charge stored. So most of the capacitors that we're going to be working with that you'll see around will be on the order of microfarads or even picofarads. So remember that if you have a 1 farad capacitor, you have a deadly weapon in front of yourself. Okay. So now that we have figured out kind of the theoretical properties, let's see if we can apply that to come up with an expression for the capacitance in terms of those physical properties. So let's go back to black here. So here's my plate, here's my capacitor, and we're not going to draw the part that's connected to the battery down here, but I've got D is the distance between them, and then I've got the area, and we know that it has to depend upon that. Okay, now we could reconstruct how all that works using our pluses and minuses, does it increase, decrease, and all that, but we can also derive it theoretically, and that's what I want us to do now. So let's start with this definition here. So C, the capacitance, is defined to be Q over V. All right. Now we have defined Q. We can get Q from the area charge. Let me just go ahead and write that out like this. So that's the area charge density. And so that tells me that Q is going to equal this. Now you may say, well, why did you do that, Dr. K? Because remember, I want to express this in terms of area and the plate separation. So I look through my notes and I'm trying to find, okay, what will apply to this parallel plate capacitor? It has to apply to a parallel plate capacitor. Don't start trying to use point charges and things like that. Not everything is going to apply here, but this certainly does. The area charge is going to be the charge density that times the total charge is going to be the charge density times the area for here. So I'm going to substitute that back up in there. So let's put this over here. So C then is going to equal sigma A over V. Well, I need to get rid of that V, and I want to express it in terms of D, and I want to express it in terms of A. What would be an expression that we've worked with before that would give me one of those kinds of things? Well, we've already used A, so we're probably not going to introduce another one. So we can use D, and we've talked about this before just a second ago. E times D is the voltage. So I'm just going to substitute this right in. So that tells me that C is sigma A over ED. Well, I still want to get rid of that electric field. So the last thing I need to do then is to get rid of that electric field. Okay, well, we just found the expression for an electric field. And for one of the plates, we decided it was sigma over 2 epsilon naught. That's for one of the plates, but we have 2. So the total electric field is going to be due to 2 of these plates. So let's draw that. Let's think about that right quick. Let's say that this is the positive plate. And let's say that this is the negative plate. All right. Looking just at the positive plate, what does the electric field look like? Can you draw that with your hands or sketch it on a piece of paper? Well, according to Faraday's rules, it's going to come out like this. All right. We're only concerned with what's going on in between, so I'm not going to draw all the ones on the other side, just in the interest of time here. So we're only interested in the electric field between the plates. Okay, how about for the negative plate? What does its electric field look like? Well, according to Faraday's rules, that one's coming into the charge, like this. So it's coming into the negative charge. E is a vector. I can add that vector. And it turns out that since both of these are only in one dimension, then I can simply add their magnitudes. And so the total charge then is simply going to, the total electric field is simply going to be the electric field of the top plate plus the electric field of the bottom plate. But we know that these electric fields are both given by this expression. It's just I may have a positive and a negative charge density here. So the total electric field then, which we're going to call E total, then it's going to be two of these, sigma 2 over epsilon naught plus sigma 2 over epsilon naught. And you should be able to see that that means that the total electric field then must equal sigma over epsilon naught. So let's put that back over here, because here we're talking about the total electric field. So C then is going to be sigma A divided by sigma over epsilon naught times D. I'm going to flip this and multiply. And so I get sigma A epsilon naught divided by sigma D. And now you see that those cancel. So for the capacitance is determined only by the area and the plate separation. This is a constant of the universe. It's not going to change. So for any given capacitor then, we'll write it up here, the capacitance can be determined from its physical properties. And this matches what we found before. We said that if I have a large area, I can store more charge. So its capacitance must be higher. If I have a short distance, a small plate separation, I can also store more charge, which means that my capacitance must be higher. So we've got a couple of different expressions for it. Here, this is for the physical parameters. Here, this is in terms of the charge and the voltage. And we'll have cause to use both of them. In fact, sometimes I may want to know how much actual charge is here. Well, I know that they're both the capacitance, so they must be set equal to each other. So I can set these two equal to each other and maybe solve for the charge for a given voltage. So that's a useful trick for you to be able to use. So keep both of these in your flip books when we're talking about capacitors. All right, so the last thing that we want to talk about here is going to be the energy stored in a capacitor. Let me get me in a clean area here. Get the camera back. There we go. So let's think about this for a minute before we get too far into it. Now, we know that the electrical energy, electric potential energy, is Q times the electric potential. And if you don't remember that from previous lessons, go through your notes because that's a really important result. So in my circuit here, we might kind of naively say, oh, okay, well, the voltage doesn't change. So as long as I know how much charge is here, I can get my electric potential energy for that. Unfortunately, that doesn't work because let's think about this. Conservation of energy says I have to do work against this. Well, let's say that I've got a switch here like this. All right. When I first turn on that switch, is at the instant I turn it on, is there any charge on these plates? Well, no, right? Because until just that instant before, I didn't even have the switch was open. I didn't even have any charge to move around. So I had no charge on these plates. So this first unit of charge that moves over here, and then of course I'm going to end up having a positive here, it's not moving against an electric field, so it does no work. There's no electric potential energy there, so that charge moves for free without any work at all. Now, as soon as that charge is there, do I get an electric field? Yes, I mean, it's tiny, it's not very strong, but it is there. And it's going to go from the positive to the negative like that. So that means that the next little bit of charge, the next unit of charge that comes through has to do a little bit of work. Not much, because it's working against just a tiny electric field from there. But now that has increased the electric field. So hopefully you can see that as we add charge, it gets harder and harder and harder to add that charge. And so I have to do more and more work. So by the time I'm fully charged, the amount of, I've got my total charge on there, my total Q on there, but the amount of work I had to do was not constant. I started out with almost nothing, and then it went really high from that. So I can't simply say this is going to be the final energy. It doesn't work that way. Instead, what we have to do is we have to integrate it. We have to follow those little pieces. So we'll write this in integral form. So we'll have d UE, and this is just a standard differential, not a partial. is dq times the voltage, and that's the voltage across the capacitor, remember. So we'll just remind ourselves by the cap. So I'm not talking about the voltage of the battery, the 9 volt or whatever, that's fixed and we're not going to change that. But we're studying the voltage across the capacitor, like that. All right, now here again, you might say, okay, fine, I can integrate this and I'm good to go. And you're going to end up getting right back to this expression as soon as you integrate it. However, the electric potential we've discovered depends upon how much charge we have available, right? So we've done that before. So I'm going to need to use that expression. Well, the easiest way to determine how the electric potential depends on charge is to talk about the capacitance. So the capacitance is Q over V. Stop for a minute and let that sink in. That's the expression we just derived. Does the capacitance for a given capacitor, does it change? Whether the power's on or off, does the capacitance change? It doesn't. And the reason for that is because the capacitance is also determined by its physical parameters. And those physical parameters exist whether there's charge moving through it or not. So the capacitance is fixed, and that's why this expression here is a good choice. So let's solve this for V, because this is going to be the voltage across the capacitor. Now, in our little shell, we've used a Q. Here we used a capital Q. Here I've used a lowercase q. It doesn't matter, but we want to keep our symbols the same. So I'm going to write this then as C is Q over V cap. And now I'm using the same symbols that I'm using here. So let's solve this for V. And that tells me that V cap equals Q over C. And C is a constant. So let's plug that back up in here. And so I have dUE equals dQ times Q over C. Now we're ready to integrate. So we're going to write the integrals here. And these are standard integrals. They're not path integrals or surface integrals or anything like that. So this is dUE from 0 to my final UE. Now, the math majors are going to really grump about me using the same symbol as a limit of integration is here, but hopefully you can see what I mean with that. And then this is going to be the integral of Q over C dQ. Well, C is a constant, so I can pull it outside the integral. And that gives me Q dQ. Well, integrating this one, you're just going to get delta UE, so the change in electric potential energy. Remember, anytime we have this construction where I have the integral of D of something, it's going to turn out to be delta UE. And go through the integral and you can convince yourself if you don't remember why that's true. Now, you should also be able to integrate Q dQ. So that's going to be 1 over C times, and this is going to go from 0 to the total charge. So that's going to be 1 over C times 1/2 Q squared from 0 to my total charge. Let's write that out a little bit separately. So that's going to give me Q squared 1/2 Q squared over C, just like that. Now, this quantity, the delta UE, you also know that that's also the work. That's how much work I have to do to actually charge this. So that if I started with 0 potential energy, the potential energy I have at the end of the day, as soon as this thing is fully charged, then it's going to be UE. So this is one expression for the electric potential energy that is stored in the capacitor. Now, most of the time when we're doing this from a practical standpoint, I don't know how much charge is there. Usually I know the voltage, I know the current, we'll talk about later. I know the capacitance. So we want to express this also in terms of the voltage. So I'm just going to go right back to my friend here, and I'm going to plug that back in. I'm going to solve this for Q. So let's do that in the side over here. So C is Q over V, where V is the voltage in the capacitor once it's fully charged. And so that means that C times V is going to be equal to Q. So I'll plug that in over here, and I get UE is 1/2 V squared C squared divided by C. You see that one of my C's will cancel. And so another, let's write it directly below, another equivalent expression for the electric energy electric potential energy in a capacitor is 1/2 CV squared. Which one you use depends upon what you're given and what you're looking for. So you should have both of those. All right. So those are two ways of getting the electric potential energy. Since they're both equal to the same value, they're also equal to each other, but that doesn't do a whole lot for you. That's just going to get you back to this expression right here where we started from. Just remember that C is a property of the physical properties of the capacitor, how close the plates are spaced, and then the area of that plate itself. Okay, so there's one more thing we need to talk about. So I've cleared the board here so that we can do this. What if I wanted to make a really, really large capacitor, something that, I can't find anywhere? I've got a limit to how, all I've got is maybe a 10 microfarad capacitor, and I want to have 50 microfarads or something. So how would I be able to do that? So take a look at microtest 5 then, and let's think about what's going on with this. So suppose I have this circuit, and I'm going to have 3 of these capacitors, and they're not necessarily the same. We're going to wire them up in series like this so that we would think that, okay, now I've got a big supercapacitor because I can just think of this as being one big capacitor. All right? And so we've got our left capacitor, our middle capacitor, and our right capacitor. So let's see if that actually works. So take a look at the multiple choice, the circling down there next. It says, so how is the current through the left and the right capacitors related? How is the current through those left and right capacitors related? So current comes in here, and this is the left one, and this is the middle one. Sorry, comparing the left and the middle one to start off with. We'll do the right one in just a second. So I have current that goes to there and current that goes to here. And you might say, well, no, there's no gap here. Well, remember, we've talked about it, how it's pulling those charges along. So how would the current through here compare? They actually have to be the same. And we'll deal more with this later on, but that's called the charge continuity principle. And it's because charge is a thing. It can't just vanish. And so any current that comes in here, any charge that comes through here, also has to be through here. So it's got to be the same. I've got to have the same amount going all the way across here. So now when you look at the next one, we compare the middle to the right. Well, okay, those have to be the same too, because it's coming through. So we know that the capacitance depends upon the charge and the volume. And so we wrote that as Q over V equals C. That's the general rule for the capacitance. So we might call the total capacitance maybe C tote and Q tote and V tote. Okay. Now, the voltage drop across here is probably not going to be the same. But because if you think about it, if you remember our light bulbs, as I go from here to here, I'm going to use some of that potential energy. And as I go from here to here, I'll use more of it. And as I go from here to here, I'll use the rest of it. So if this is the total voltage here, it's going to be different for each one of those capacitors. It's just going to slowly step down. The total voltage across the entire thing must be equal to the voltage here. All right, so let's write down, let's solve this capacitor equation for V for each one of these. Okay, so we have V tote then is going to equal Q tote over C tote. And we can do a similar thing for the actual capacitors. The voltage across the left capacitor must equal the charge across the left capacitor, which is equal to the capacitance of the left capacitor, and then similarly for the middle and for the right. So nothing earth-shattering there. All I've done is I've just taken that base equation, I've rearranged it for all of these. Now, as we said, the total voltage from here to here must equal this total voltage here because they've got the same electric potential. So that means that the voltage from across here, which we've called VL, plus the voltage across here, which we call VM, plus the voltage across here, which we call VR, must add up to V total. So let's write that down explicitly. So V total has got to equal V left plus V middle plus V right. Now let's take these expressions then that we substituted in. And that's what the next block in the microtask is asking you to do. So that's going to be Q tote over C tote And then same thing for the left and the middle and the right. But we just decided that the charge, the current through all of these must be the same. If the current is the same, then the charge must be as well. So all of these Q's then are the same. So I can just divide them out. And what I'm left with is 1 over C tot equals 1 over CL plus 1 over CM plus 1 over CR. And that is the expression for combining capacitors in parallel. So let's clean that up just a little bit. Okay, so is the total capacitance then equal to the sum of the individual ones? Well, it's not, right? And in fact, what you're going to find when you add these up is that the total capacitance actually goes down. And you should try some to experiment with that. The total capacitance in here is going to be less than any of these individuals. So if this was 10 microfarads and this was 20 microfarads and this was 5 microfarads, then the total capacitance is going to be less than 5 microfarads. And you should try that out. Plug those numbers in and see what you get. Here's a caution. What a lot of students forget, they'll do 1 over 10, 1 over 20, 1 over 5, times 10 minus 6, but then they'll forget to invert it back. You could get common denominators and add all these up, and you would get something like CL CM CR over CL plus CM plus CR. And that's perfectly okay. But on my calculator, I've got an invert button, 1 over X. Yours might be X to the minus 1. It's easier for me to take 10E6, 1 over, plus 20E6, E minus 6, 1 over, plus 5E minus 6, 1 over, equals, and then hit that button again to do 1 over, and now I've got my C total. You do you, whatever works out. So the key thing we want to realize here, though, is that putting them in series does not make a supercapacitor. In fact, it makes a weaker capacitor, which you might want. Maybe you need to bring down the capacitance and you just don't have a capacitor that will do what you want. That's fine. Then you just put them in series and you'll bring the total down. All right. Well, okay, we really do want to build our supercapacitor, so take a look at microtest 6. If they're not in series, then we can say that maybe they're in parallel. And so that's the circuit that we have drawn here. They're in parallel, like this. And hopefully you can see why we call that parallel, because, well, they're parallel to each other. The other thing to think about, they're in series if all the current that goes into one goes into the other. But if you look here, and let's change colors. If you look here, the current that comes in through here has to split, and then it splits again. And so the current through each one of these capacitors cannot be the same as the original current. So that's our definition of being in parallel. If the current doesn't split, so if all goes into one and goes into the next one, then they're in series. If it does split, they're in parallel. So no matter how you draw them, you don't necessarily even have to draw them so that they're lined up parallel like this. As long as it splits, you know that they have to be in parallel. Okay, so this is my voltage again, and this is my total voltage. And now, because I don't have left, right, and middle, we'll call this C top, and we'll call this C middle, and we'll call this C bottom from that. Okay. Now, the charge is not the same, but the voltage is. And you should be able to see that the voltage across each one of these capacitors is the same because, well, you know, if I connect my leads here, that's just a wire back to the battery. If I connect here, that's also just a wire back to the battery. If I connect here, that's a wire back to the battery. So the voltage for each of these, so for V top, VM, and V bottom, all of those are equal to V total. If you're not sure about that, stop the video and think about that, because that's going to be key to what we're doing. Okay, so all of those voltages are the same. So what we want to know then is how are these three capacitors related to each other? Well, I know, just like I did with the potential drop, we said that all of the charge that goes in here must equal the sum of all the charges going in here. And we called it current, but remember, current is just charge per second. It's just how fast it's moving. So you can kind of think of them almost as interchangeable. So all of the charge that goes in must equal the sum of everything that goes out. So let's write that explicitly. So Q total must equal the Q through the top plus the Q through the middle plus the Q through the bottom. Okay, in a similar way to what we did before, let's take our capacitor equation. It's Q over V. And now I want to solve it for Q. Well, that's really easy. That's just CV. Okay, let's take that and plug that in over here. So I get C total, V total equals, oops, we want C, not Q, equals C total, V total plus CM, VM plus CB, VB. Running out of room there. But we just said that all of these voltages are the same. So I can cancel all of those out. I can just divide them out. And so I'm left with C total equals CT plus CM plus CB. And that is the equation for capacitors that are in parallel. So now what we can say is we've asked, does the capacitance, the total capacitance, equal the sum of the individuals? And the answer is yes. So anytime you need to build your supercapacitor, wire them in parallel. And then if I've got all of them in parallel like this, then I can simply add up their totals, and that's going to be my final answer. So now we've talked about pretty much all we need to know about capacitors with that. We've talked about how we figure out how much charge is stored on there. We've talked about how we build the capacitor and how those two things, the spacing and then the area of the plate, are going to determine how much charge you can store. Once I know how much charge I can store, then there's some manipulations I can do for a given amount of potential energy. What's my capacity? What's the amount of charge I can store? What's the potential energy that comes out at a particular voltage? All of these are questions that we can answer using these expressions that we've derived. So it's a good idea to have a separate page in your book on capacitors and just everything that you've learned for that, so that anytime you're working with a parallel plate capacitor, you're just going to go straight to that and you'll be ready to go. All right, so take a look at the problems. Most of them, remember, are very straightforward. You should be able to just take these results that we've derived here and apply them to the situation. And as always, if you have any problems or questions, make a discussion post and let's talk about it. All right, we'll see you next time.